Right, 7.3, volumes, part B. I did make a boo-boo when I copy and pasted on your notes. I copied the wrong one. I meant to do vertical. So your paper says, I think it says AB, and it has an X. Well, obviously, if we're revolving vertically, right, on the coordinate grid, the y-axis is vertical. So it should be pi times the integral from c to d of r of y squared dy, because it'll be with respect to y. My bad. Okay, so example 1. Here we have a graph, which we're going to revolve around the y-axis. You see the little arrows down here? And revolving this around the y-axis is going to give us some kind of solid figure that looks like this. Now, we have the equation, which is y equals x squared. But I'm revolving around the y-axis. That's vertically. And around the y-axis, I need my equation to be x equals something. Normally, we have like y equals 3x squared or y equals 5x, whatever. But for this, revolving around the y-axis, I need my equation to be x equals something. So the equation that they gave us is actually not going to work out for us. I'm going to have to make this into x equals something. And so to get rid of the square, I would square root. So x equals the square root of y. And that is the equation I'm going to use. Because when we revolve around the y-axis, we need to be in terms of y, because we're going to integrate with respect to y. All right, so volume is equal to pi times the integral from c to d. Now, if you recall, when we did area underneath the curve for y or x equals with respect to y, we had to do the right curve minus the bottom curve, right? And we used the y values for the limits. Okay, so similarly, we're going to use the y values for the limits. So this is going to be from 0 to 4. My equation now in terms of y, which is what I need, x equals the square root of y, that is what we're going to use. So it'll be the square root of y squared. And then this is with respect to y, so dy. Okay, so beautifully, that square root of y squared becomes y, which is nice. And then this is what we're actually integrating. So pi, integrate y, we get y squared divided by 2. And then this is being integrated or evaluated, sorry, from 0 to 4. So now we plug in the 4, we plug in the 0. So let's see. Plug in 4, I get 4 squared divided by 2, so 16 divided by 2, which is 8. And then plug in the 0, we get 0. Voila. The volume is 8 pi. That's a horrible pi. Sorry. Let's see. 8 pi. There we go. And that is the volume of this solid that is generated by rotating around the y-axis. Okay, example 2. Evaluate the integral that gives the volume of the solid formed by revolving the region about the y-axis. Again, same thing. The only difference here is, if you look, this function is actually being cut right here. Now, that is okay, right? It's no big deal. It's just going to look kind of like, let's see if I can draw this. Okay, I can't draw it, but it's going to look like this. If it's revolved around the y-axis, it's going to look something like that with a flat bottom. Okay, so in order to evaluate the integral, I need my equation to be x equals something, and it is. Yay, we like that. The formula for volume is pi times the integral, and this is going to be from 1 to 4. And then my equation is negative y squared plus 4y, and that's going to be squared dy. Okay, now you see the negative y squared plus 4y squared, that quantity squared? We're actually going to have to figure out what that is. So negative y squared plus 4y times negative y squared plus 4y. We're going to FOIL that, and we're going to end up with y to the fourth minus 8y cubed plus 16y squared. Okay, so that is what's actually going to be integrated. Okay, we don't try to use substitution, or use sub, or anything like that. Just FOIL it out. It's really not that difficult. So my integral from 1 to 4 dy, and this is what we're using. Ooh, almost perfect. Look at that. Okay. So we're going to integrate that. So then I get y to the fifth divided by 5 minus 8 y to the fourth divided by 4 plus 16 y to the third divided by 3. And of course, we're going to evaluate this from 1 to 4. We're going to plug in the 4 and then plug in the 1 and subtract. Obviously, the only thing that can be simplified is the 8 over 4, because that's actually 2, so it's 2y to the fourth. But everything else is pretty much what it is. You're going to plug in the 4, you're going to plug in the 1. Of course, I already have this done, so I'm just going to write it down. If you want to double check my work, that's perfectly fine. So we're going to plug in the 4 first. And we get 4 to the fifth divided by 5 minus 2 times 4 to the fourth plus 16 times 4 to the third divided by 3. And then minus, and we're going to plug in the 1. So 1/5 minus 2 plus 16 over 3. And I think it's safe to assume that a problem like this with such big numbers, like 4 to the fifth divided by 5, calculator can be used, and when you plug all of that into the calculator, I got 30.6 pi, and that would be the answer. Of course, you can turn it into a decimal if you choose, but you really don't have to. So that is the volume of this weird shaped solid. Okay. Example 3. Find the volume of the solid generated by revolving the region bounded by the graphs of the equations y equals x, y equals 0, y equals 4, x equals 5, about the line y equals 5. So that might sound weird, but let me read it again without reading any of the equations. Find the volume of the solid generated by revolving the region bounded by the graphs of the equations about the line x equals 5. So these equations, right, whatever area is generated by them, we're going to revolve that around x equals 5. So we're not revolving across x axis or the y axis. This is actually a line x equals 5. But it is still vertical. So it's still the same formula. So I'm briefly going to graph these equations. Okay, it's always a good idea. X or y equals x is a vertical, or not vertical, sorry, a diagonal line. It hits out 1, 1, 2, 2, 3, 3, 4, 4, like that. We do have to use y equals 0, y equals 4, so, and x equals 5. So let me go ahead. 1, 2, 3, 4, 5. And then 1, 2, 3, 4, 5. Okay, so this should be 5, 5. Okay, I'm a little off. But let's make pretend that's 5, 5. Maybe I can adjust it. Come on, red. Oh, I can. Ah. Okay, so there is my 5, 5. All right, y equals 4. Let's see where that is. 1, 2, 3, 4. Here's y equals 4. Right? X equals 5. Let's see. 1, 2, 3, 4, 5. Here's, oh, that is not a straight line. There's my x equals 5. And then y equals 0. Let's do that in purple. Purple. Y equals 0 is this right here, right? So, first of all, the area that is enclosed by all of these graphs is the area that we're going to be revolving across x equals 5. So this blue line, that is actually where we're going to revolve across. Okay, so it's going to go around like this. And the area enclosed by all of these graphs is this section right here. Okay, this is the area enclosed by these 1, 2, 3, 4 equations. So when I do revolve, it's going to look something like this. That'll be the top. It'll be nice and flat. And then the bottom will also be nice and flat. And it'll be slanted like this. Okay, that is what it's going to look like when it revolves. And it will be a solid, right? And it'll be revolved across x equals 5. I use the word about. Okay, so in order for me to figure out what the equation is, we're going to have to go back to finding the area underneath the curve. Now, if you notice, this is a lot nicer if we use y equals 0 and y equals 4 as the limits, right? Because we are going across the x-axis, or sorry, the x equals 5, not the x-axis, x equals 5. So just like the previous examples, we're going to use this in terms of y, right? Our limits are going to be 0 and 4, right? 4 is here, 0 is here. And I don't remember what section it was from chapter 6, or was it section 1 of chapter 7, but area between these curves, when we're dealing with respect to y, it's not the top minus the bottom, it's the right curve minus the left curve. That is how we can find the area in between. So the right curve is basically x equals 5. That is the curve on the right, or the line, if it makes you feel better. So 5. And then the left curve is actually the red equation, which is y equals x. But if we're dealing with in terms of y, we're going to treat that equation, this one right here, we're going to treat it as x equals y. Obviously, I'm just saying it backwards, right? So it's 5 minus y. Okay, that is the equation that we're going to need here. Because you take the equation, right? You square it. But here we had so many equations, we had to figure out what the equation would be that we were using. And so it's 5 minus y. Okay, this is going to be r. And r is just basically radius. Because if you think about it, this solid here, if it was just x equals 5, right? It would look like this. It would be a big fat like square rectangular shape. And then when we revolved that rectangular shape, and I'm going to go back up, guys. I just want to explain. That rectangular shape would end up looking like this, one big fat cylinder. But see, then the red line is just a triangle, right? So it would actually just be this part right here. So then when you revolve that across x equals 5, you would end up with, okay, I'm sorry for the drawing. Yes, it's going to be butchered. You would end up with a triangle being turned over and over and over again. So, and please, I am not an artist, right? We know this. Ooh, yeah, that looks horrible. Okay, let's fix it a little. Okay. So it would be this really big shape, right? Be this round shape. But then in the inside it would have a hole. And that hole would be the shape of this right here, which is what we're actually looking for, right? So if you think about this, I only need the inside of this. And I'm sorry if my picture doesn't look like what it's imagining. To me, it kind of does. I need the inside of it. The blue thing would get me an entire solid cylinder. The red would be everything but the actual thing I need. So if I take the blue and I subtract all of the red from it, I would end up with this, which is what I needed in the first place, right? Hopefully you understand what I'm saying. Goodness gracious, this should be a little higher, right? So what I'm saying is I would subtract all the red, which would be all of this part right here, and then what would be left over is the part I actually need. So that's why it makes sense to take the blue, right? The blue part is the 5, subtract the y, oh, yeah, the y, and that's the red part, and I would be left with the black part. Okay, my pictures are horrible, but hopefully you can kind of tell what is going on. All right, so now that I actually have an equation, volume is still going to be the same. It's going to be from 0 to 4, and then my equation is 5 minus y, and that's what I'm going to square, and then I am integrating with respect to y. Okay, 5 minus y quantity squared, yes, FOIL it. So when we do, we get 25 minus 10y plus y squared, and then we're going to integrate this. So 25y minus 5y squared plus y cubed divided by 3. And then that is evaluated from 0 to 4. And I'm going to cheat a little. So I'm just going to go ahead and simplify it. When I plug in the 4, when we plug in 0, we get 0. When we plug in 4, we get 100 minus 80 minus 64 over 3. And then when we plug in 0, we get 0. So you simplify that, your answer is 124 pi divided by 3. Okay. So here, we're going to revert back to horizontal axis, right? But sometimes we end up with like a circle, and then you subtracting a circle out of it. They call this the washer method, right? If you know anything about like nuts and bolts, you know, a washer is a little piece of metal like this with a little hole in it. And in the washer method, all it is, if you look at this picture, ladies and gentlemen, here I have a circle. And in this circle, I am deleting, taking out another circle. The formula for a circle is pi r squared. If that's my first circle, the big one, and I'm subtracting the little one, oh, let's not use r, because if I use r again, how am I supposed to know which one's which? Ah, genius, right? So let's use big R for the first one, right? Pi r squared, that's a big R. And then we'll use a little r for the little circle. So basically, we're finding the area of the big one, subtracting from the area of the small one, but we're integrating, so it actually ends up being volume, right? And, oh, they both have pi in common. So let's go ahead and pull out the pi. Oh, look, big R squared minus little r squared with a pi. And then we are going to integrate because it's volume. Oh, but you know how I am. Mrs. Ronan loves putting constants outside of the integral. Okay, I hope you see what I'm getting at here. This is just basically circles, and we are subtracting a circle from another circle. And then we're integrating in order to make the area into volume. That's it. So the washer method is the outer circle minus or the inner circle. And so that'll be 2 equations. You do have to sometimes, though, figure out what is the radius. And the radius is usually an equation. Sometimes it's actually just a number. All right, so proceeding. Here we happen to have the graph, so fantastic. Find the volume of the solid formed by revolving the region bounded by the graphs of y equals the square root of x and y equals x squared about the x-axis as shown. So this time we're back to revolving horizontally. Right, it's going to go around the x-axis. So this weird looking thing, which kind of looks like a pedal, is actually going to turn this way, right, and then come down here. And it's just going to keep turning and turning and turning to the point that it's going to have an outside, a solid outside, but then it is going to actually be hollow. Okay? Hopefully you have a really good imagination and you can see what I'm saying. But basically it's going to be hollow. And on the inside, it's going to look like this on the inside. Okay? Right. Now, find the volume of the solids formed by revolving the region, these two equations. Basically, figure out which one is the outer one. Obviously, it would be the one on top, right? So when we do the volume is pi times, this is going to be big R. Okay, this right here is big R. And then this right here will be little r. So the square root of x squared minus x squared squared. And then this is getting integrated with respect to x. And then, of course, we need our limits. And our limits are 0. Oh, I circled the wrong 0. There we go. 0. And 1. All right, so square root of x squared is so beautiful because it just becomes x. X squared squared is x to the 4th, right? Because it's 2 times 2. And then dx, and so go ahead and integrate. So x squared divided by 2 minus x to the 5th. Oof, that does not look like an x. X to the 5th divided by 5, and evaluating it from 0 to 1. So obviously when you plug in 0, you get nada. When you plug in 1, you get 1/2 minus 1/5. Now this is a kind of problem that I would expect you not to do with a calculator. Like you wouldn't need a calculator for this problem. There's no reason why you cannot do 1/2 minus 1/5. Okay? You could even do decimals if you like. For example, 1/2 is 0.5. 1/5 is 0.2. Okay, what's 0.5 minus 0.2? Oh, 0.3. So my answer is 0.3 pi. Or 1/2 is also the same as 5/10, and 1/5 is the same as 2/10, right? Common denominator. 5 minus 2 is 3/10, and then there's my pretty little pi. So 3/10 pi or 0.3 pi. Same thing. This is a problem that you shouldn't have to use a calculator. And that is the volume of this, what is this? Of this, I guess, solid revolved around the x-axis. Okay, example 5. Find the volume of the solid formed by revolving the region bounded by f of x equals 2 minus x squared and g of x equals 1, about the line y equals 1. Okay, so we have a graph, right? Now, if you notice, our limits are pretty easy to find, but there is a way to figure out where these two equations would actually touch. I've done this before, and the way to do it is basically set them equal to each other. If you set them equal to each other, you can find where they intercept, and those would be my limits. Okay, so 2 minus x squared, and like I said, we have a graph so I can see it, but just in case. So let's see, subtract 2 from both sides. I get negative x squared equals negative 1. So get rid of the negatives. X squared equals 1. So x is actually plus or minus 1. Ah, so there's where they intercept. Okay, these are the x-intercepts. So those would be my limits. Then also, I have to pay attention to the fact that all the other previous scenarios, right? All the other examples, or I guess the previous one anyway. There was a hollow solid, right? This thing back here, right? It was hollow. So that's why we use the washer method, because there's like an outer and an inner circle. Well, this thing is also going to be hollow, but we are revolving across the x-axis, I believe. Oh, about the line y equals 1. Sorry. We're revolving around the line equals 1. I didn't read. So when I revolve across y equals 1, right, I'm kind of cutting. I'm cutting the equation, or the original function. F of x minus, or equals 2 minus x squared would have probably looked a little more like this, right? So I'm cutting a piece out of that. And so I can't just use f of x equals 2 minus x squared. I can't use that equation. That equation won't serve as my radius because I am cutting a piece of it out. So you have to keep that in mind. I need a radius. That equation is not going to work. So because I cut off at y equals 1, or g of x equals 1, same thing. In order to find the radius, right, I have to use f of x, but then what I cut out of it, I kind of have to keep that in mind and compensate for that. So what was cut out? Well, 1 was cut out. And the words cutting out should tell you, was that addition or subtraction, right? It was subtraction. So to find the radius, I actually have to figure out what my equation is going to be. So 2 minus x squared minus 1. So 1 minus x squared. This right here is my radius. This is what I'm going to use to find the volume. Okay, because if I just use f of x equals 2 minus x squared, then it's going to think I'm using the whole thing, right? And I'm just revolving across the x-axis. But that's not really what's happening. What I'm using is up to here, and I'm revolving across that, y equals 1. So you figure out what your radius is by taking out, subtracting, whatever my y value is, the where I cut off the graph. Now, if this was my graph, and it did continue on like this, and I decided to revolve it across y equals -1, guess what would happen there? I would have f of x minus -1, so it would actually add it, because I am adding a piece to the graph. Okay, so anyway, now we just do volume, and that's the easy part, I hope, anyway. Volume equals pi. Now my limits, -1, 1, and the equation I'm actually going to integrate is 1 minus x squared with respect to x. So, FOIL, please. And we get 1 minus 2x squared plus x to the 4th. And that, ladies and gents, are what we're actually going to integrate. And when you integrate it, you get x minus 2/3 x cubed plus x to the 5th divided by 5. And that is getting evaluated from -1 to 1. Oops. From -1 to 1. Okay. Plug in 1, plug in -1. I'm going to cheat a little. When I plug in 1, and this is a little simplified, because, I mean, this is just arithmetic, folks. I get 1/3 plus 1/5. And then, oh, let me not skip that much ahead. I get -1/3 and -1/5 when I plug in -1. You are more than welcome to check that, right? And then I did further simplify this. This is actually another one that, in my opinion, you should be able to do totally without a calculator. As you can see, I made 1/3 and 1/5 into 5/15 and 3/15, so I can get 8/15. And then negative 1/3 and negative 1/5 become 5/15, negative 5/15, but because of this negative that's already there, well, first of all, I have to, what's the word? Distribute. These become positive, right? So positive 5/15 and then positive 3/15 for another 8/15. And then, ooh, 8 plus 8 is 16. Oh, that's a 5? Wow. 1, 5. 8 plus 8 is 16 over 15. So 16 over 15 pi. Right, next. Okay, last one. We have somewhat of a graph. This is actually the entire solid. Okay. A manufacturer drills a hole through the center of a metal sphere of radius 5 inches as shown in the figure. The hole has a radius of 3 inches. What is the volume of the resulting metal ring? Okay, it does go through the center. So it is fair to say that this is going through 0, 0. Now remember, this is just circle minus a circle. Okay, so I do need equations. I need an equation of the big circle and an equation of the small circle. And the big circle, right, has a radius of 5 inches. And it goes through the middle. And if you remember from geometry and from calculus, pre-calculus, and from algebra 2, the equation of circles is x minus h squared plus y minus k squared equals r squared. Now for the big one, it does go through 0, 0. That's the center. H and k are supposed to be the center. So since it's 0, it's just really x squared plus y squared. And then they told us the radius was 5, so 25. Now, we are revolving across the x-axis. So I need an equation, not x squared plus y squared equals 25. That actually does me no good. I need an equation that's y equals something, something, something. So you're going to take this equation and you're going to solve it for y. So y squared equals 25 minus x squared. Got to get rid of the square. So y equals the square root of 25 minus x squared. And here, folks, is my big R. Okay, so the circle, the big circle, that is the formula of the big circle. So now I need an equation that represents the inside circle, Remember, this is getting revolved, right? So obviously, if you revolve a circle over and over again across the x-axis, it should look like a sphere, shouldn't it? But the inside of the sphere is not a smaller sphere. It's actually like a tube. Right? This is a tube. So let's see, what would my equation have to look like in order for me to revolve it over and over again and it be a tube, a cylinder? So hopefully you're thinking, oh, it's a rectangle. I probably went too far there, but it's a rectangle. And it is a rectangle. It's basically just a rectangle. So this area can be determined by using this equation right here. Okay? That inner tube has a radius of 3. So then this makes it y equals 3. Now, I do need to figure out where those two graphs actually touch. Because what I am actually revolving here, folks, what is being revolved, believe it or not, is this piece. This piece right here is being revolved over and over and over again across the x-axis like this. And that little piece is what made this hollow sphere. Okay, so in order to find the volume, I need big R. We found big R. Big R represents this part right here. And we need little r. Okay, so little r is going to be this right here. Oh, that's y equals 3. So volume equals pi. We don't know our limits yet. From the picture, you can kind of tell, but we're going to actually verify it mathematically. Big R is going to be the square root of 25 minus x squared. Let me use brackets. 25 minus x squared squared minus little r squared. And little r is just y equals 3. The equation is 3 squared. And this is, of course, with respect to x. Now our limits. Like the previous example, take the equations and set them equal to each other. That doesn't really work, right? Maybe. I could make this 3. Let me show you what I'm talking about. La 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 la. I could plug in a 3 here. But then I have to square both sides. So maybe the better idea would be to plug in the 3 here. Right? Or here. It actually doesn't matter. Go ahead and plug in the 3 into one of, oops, that's supposed to be not highlighter anymore. Go ahead and plug in the 3 into one of these. Pick one, whichever one you like. The bottom one is probably the better choice. Although, honestly, it doesn't seem to matter, I don't think. Okay, so I'm going to do the top one. X squared plus 3 squared equals 25. Subtract 9 from both sides. Oh, x equals negative and positive 4. So those are my limits, negative and positive 4. Okay, you're just trying to figure out where they intercept, where they touch. Basically, this right here. Where is this and where is this? Okay, and that is positive and negative 4. So negative 4, positive 4. And you're going to integrate. Now the beauty here is that the square root of 25 minus x squared becomes just 25 minus x squared. That's nice. Minus 9. You're still integrating. So then you do actually integrate. Oh, and of course, 25 minus 9 is 16. So 16 minus x squared is what you're actually integrating. And so we get 16x minus x cubed divided by 3. And then we're evaluating this from negative 4 to 4. And this is one that I would strongly feel as though they will let you use a calculator on, because the fractions and the numbers aren't as friendly as the previous 2 examples. Right? The previous 2 I said? Yeah, the previous 2. So with that said, I'm just going to go ahead and tell you that the answer is 256 pi divided by 3. So hopefully if you pop that in, if you plug in 4 and negative 4 and you pop it into the calculator, you'll get a decimal. Or if you actually do it manually, as I did, you'll get 256 pi divided by 3. All right, that's that. We'll be doing some classwork in class. The book doesn't have good problems, so no homework.